Sir, that Amina ma'am is taking revision.
Oh, so you are joining that too.
Yeah, I got that link to join.
Yeah. So that is okay. So your
So,
revision
sir,
part.
you also take the revision class.
Yeah. So okay, that I will say because
So I will join your class then.
no, because if Amna ma'am is taking the revision classes, then that is yes, that's quite and simultaneously, I will also try to some topics. Yeah, so please don't miss those classes, right? And whatever questions that you have, please ask Amna ma'am because she is a brilliant teacher, right? And even I can say that she is better than me. So yeah, whatever question that you have, please don't hesitate to ask any question, right?
Yes, sir.
Okay, so let us start from that. And in the thermodynamics, first thing that we will be talking about is the laws of thermodynamics. So, what is a thermodynamics, right? What do we understand by thermodynamics? You can see that this is made up of two words, thermo and dynamics, right? So what do we mean by thermo? Therm means what? It is related to what? Therm. Yeah. So thermo means temperature. Dynamics means the moving thing, right? So whenever we are studying the materials and their properties with respect to the temperatures, so that is called thermodynamics, right? And in thermodynamics, we have two things. What are those? One is this system, right? And then you have this phenomenon, right? So this system is defined by macroscopic variables, right? So this system is defined by pressure, temperature, and everything. So these system is defined by macroscopic variables. And what are those? So those are pressure, volume, temperature, number of moles, and so that is how we define the right, and we don't bother about the surrounding. We only talk about the surrounding whenever there is the heat and all the energies are right. Then we take into account those surroundings. But whenever we represent a system, so that is represented by pressure, volume, temperature. All those things. So those are the parameters or the thermodynamic variables in a right. So to define a system, we require pressure of the system, volume of the system, temperature of the system, and all those things. So those are called the macroscopic. Okay. And then there are laws of thermodynamics which governs the system. What are those? The first law or the first law which is called the zeroth law, right? This is the zeroth law of thermodynamics. What is that? So you have three systems, right? Let's say you have A, and then this is B, and then you have stuff, and they are connected, right? They are connected, and the heat can flow between them, right? So if this system A is in equilibrium with system B, so if this has some temperature T, right? And if this has some temperature T, and let's say it has some temperature so zeroth law of thermodynamics states that if system A is in equilibrium, which means that let's say is in equilibrium with system B, and system B is in equilibrium with system C, then zeroth law states that system A is also in equilibrium with system C. Right. So what is the meaning of that? So it is saying that if temperature A is equal to temperature B, this is first case, and the second case is that if temperature B is equal to temperature C, then it implies that temperature A is also equal to temperature C. So that is the zero. So it talks about the thermodynamic equilibrium. So if this is in equilibrium with B, if this is in equilibrium with C, so which means that this A is also in equilibrium with C. Is it clear to you?
Yes, sir.
And now let us talk about the first law of thermodynamics. And this is quite important. First law of thermodynamics. Right. So let's say you have this system, right, and then this is the surrounding. So this system will have some potential energy for some kinetic energy. So this system will have some internal energy, right? The system has some internal energy, and what you are doing is that you are providing some heat, right? Some heat from the surrounding, right? So then, what the first law of thermodynamics states that the system will do some what, right? This way, the system will do some work on the surrounding, right? And that is what we call the first law of thermodynamics. When you provide this heat, the system, so some of the energy would be absorbed in the form of internal energy, and then some of the energy will go in doing some work, right? This is what we call the first law of thermodynamics. So the heat is provided will be used in this internal energy, right? And then some amount of work would be done. Why this is? This is what we call the first law of thermodynamics. This is representing internal energy of the system. This is representing heat supplied into the system. And this is work done by the system on and surround. Right. This is what we call our first law. And this one is a very important one because from this relation we will derive our super. Right. So now the third point or the third thing is the second law of thermodynamics. So this second law of thermodynamics, it talks about the efficiency of an engine, right? Or they may be heat engine or refrigerant, right? So yeah, so this one talks about, and there are two laws. So one is called the Kelvin's, right? So we have to remember those statements, right? These statements are like so I will write those statements. You have to just exact same statements. Whenever they ask you this, so you have to write these. This is Kelvin Planck statement, and this one talks about the refrigerator. And then you have this Clausius statement. So I will write those statements, and you have to remember. Those are very complicated statements. So no process is possible whose sole result is the absorption of heat from a reservoir and the complete because we have to write this thing word to word, right? That is why we have complete conversion of heat into one. Right. So this is also related to the heating. Right. And the second one is the Clausius statement. What does it state? Say? It states that no process is possible whose sole result is the transfer of heat from a colder object, a hotter object. Right? So let us understand the meaning of these statements, right? So let's say you are no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat into work, right? So it is saying that you are providing some amount of heat and the whole heat is doing this work. The whole conversion is done in this one, right? The whole heat is used in doing some work. So that is never possible, right? The machine can never be 100% efficient. There would be some loss, right? There would be some loss due to another kind of heat, or there would be some loss due to the dissipation, and there would be always some kind of loss, right? So there's no process in which you get an efficiency which is 100%. So there is a no machine like that. So that is what this Kelvin Planck statement says. And again, the same statement by this Clausius statement. So it is saying that you have a colder region, right? This is colder, and this one is hotter region. And when you connect these regions, so from where the heat will flow? It will flow from where? Where? Yes. So the obvious thing is that where will the heat will flow from?
Cold object.
No, so heat will flow from the hotter object to the lower one, right? So heat generally flows from the higher temperature to the lower temperature, and then it is at equilibrium, both the temperature becomes equal, right? It never flows from the colder region to hotter. So that is what Clausius statement says, right? Heat will always flow from the hotter region to the colder. So these are the two statements. Kelvin Planck statement says that there is no ideal machine which can convert the whole heat. What? There would always be some dissipation, some loss of energy, right? And this Clausius statement says that the heat will always flow from hotter region to the colder region. So these are the two statements regarding the second law of Lorentz. Okay, so first law is about thermal equilibrium. Second law is about the heat flow, right? And then the third law is about the efficiency of the heat. So these are the three laws. Is it clear to you?
Yes, sir.
And you have to always, word to word, you have to always remember the best. Right? So Kelvin Planck and Clausius statement, you have to remember what was. Please note down these things, and then we'll talk about thermodynamic process, right? So please note these things down. And whenever you want me to scroll down this thing, please tell me. Whenever you want me to scroll down the screen, that
Done, sir.
yeah. Then please yeah. Whenever you want me to scroll down the screen, please
Done, sir.
yeah. So then
Done, sir.
yeah. Okay. So the next thing that we have is we have to recall whatever we studied in the thermal properties of matter or fluids, right? So what did we study in that? We studied that what is the heat capacity and what is the specific heat capacity, right? So what was that? So what did we understood, right? If we remember that heat energy was what? This was directly proportional to mass of the matter, and then this was proportional to the change in temperature, right? And then we removed the proportionality, and then we got this constant, right? So was the constant that we called was this was called the specific heat capacity, right? right? And when we took this thing together, right? So when we took this thing as a constant, and then we said that this is S, so this was called the heat capacity, right? So S was what? This was delta Q by delta T, and this was called the heat capacity, right? So let me just show you where did we did it. Right? So this was right. Heat capacity was S delta Q by delta T, and then specific heat capacity was this, right? This was the thing that we studied in thermal properties of matter,
Yes,
right?
sir.
Okay, so and back. This is heat capacity, right? And if we write this thing as if in place of this mass, if we write mu, right? In place of mass, we write mu, which is number of moles. So this was called what? This was molar specific heat capacity, right? So this is the thing. And one more equation, which is very important, and we have to remember that that is the ideal gas equation. What does it say? So ideal gas equation relates all those macroscopic variable with each other, right? So this relates all the macroscopic. This relates all the macroscopic variable with each other, and it is also called equation of state. So how do we write this? So this is PV equals to mu R T, right? Where P is pressure, P is volume, and mu is number of moles, and R is universal gas constant, and T is temperature. Right. But we can also write this thing in terms of Boltzmann constant as well, right? So how can we write this thing? So we know that what is number of moles? What is number of moles? Number of moles in terms of particles. What is the number of moles? Do you remember that? What is number of moles in terms of particles? This is the total number of particles divided by what? Do you remember that? Divided by what? the number of moles you calculate in two ways. One is mass given divided by molar mass or atomic mass. And the other thing in terms of particles, that is number of particles, total number of particles divided by what? Avogadro number, right? That is how you calculate the number of moles. You
Yes,
have,
sir.
so this is Avogadro number. And you have also this relation that this Rydberg, this universal gas constant. So this is related by this Boltzmann constant like KBNA. That is your this is the relation between Boltzmann constant, Avogadro number, and universal gas constant. Right. So you can write R as KBNA. Right. Let us write this thing. So if we put the value of, we can write this total number of particles, let's say as n by n, where n is total number of particles. So let us put these values in here. So what we will get? So PV is mu RT. Mu is how much? Mu is n by NA. And R is how much? R is KB NA and T. So NA cancel, and you can also write this thing as NK. We have seen this thing, right? So you can use either NKT. In shorthand, we can write this as K. So you can use NKT or you can use mu RT. Right? Both are correct. Is it clear to you?
Yes, sir.
So this is one thing, and then in this thermodynamic variable, so this is also defined by two specific heats, right? So those are called. So one is called CP and CP. We have a relation between CP and CP. And what is CV? CP? So CP is specific heat capacity at constant pressure. And this CV is what? CV is specific heat capacity at constant volume.
Volume.
This is the CV. And there is a very important relation between CP and CV. So CP minus CV, that is equal to 1. This is the important. And this is very useful in this chapter, right? So we use this thing in many of the calculations. This relation is very important, right? And how can we prove this thing? So let's say you have, right? So let's say you have the first law of thermodynamics, right? You have delta Q that is equal to delta U plus delta W, right? And before we talk about this thing, let me quickly talk about what is work done. Right, so work done, we know that how much is work done. This is force into displacement, right? Or let me write it as delta X, right? And
Yes.
we know that how can we write this force? So force is pressure into area. And let's write this as delta X, right? Force is pressure into area because pressure is force by E. Force is pressure into E. And this A delta X, what is area into length? That is your volume. So we can write the work done equal to P delta V. So we can write the first law of thermodynamics like this as well. So the first law of thermodynamics that will be delta U plus the P delta V. So this relation is very important. This is very important relation, right? And from this we can derive so many things, right? So when we'll talk about the thermodynamical processes, so we will use this thing exit, right? We will use this thing, we will use this thing, right? And yeah, combination of these. So please note it down, right? Please note it down and then we'll talk about the derivation.
Okay,
Quickly note it. Yeah, whenever you want me to scroll down this thing, then
done, sir.
then okay, so then please don't. Right, and this is to be precise, this is molar split. And then we'll talk about thermodynamical process, and then this chapter would be because the heat engine and refrigerator is not into syllabus. We can skip this, right?
Done, sir.
Okay. Then noted.
Yes, sir.
Okay, so now let us prove this thing, right? CP minus CV is proof of. So how do we right? So we know that what is the first law of thermodynamics, right? Delta Q. That is delta U plus P delta V, right? And we also, let's say that equation of state or ideal gas equation. So equation of state, that is what PV equals to mu R T. So for 1 mole of gas, for 1 mole of gas, this would be how much? This would be PV equal RT. This is, let's say this is first relation, this is the second relation. Right. Now, let us calculate specific heat at constant volume. So molar specific heat at constant volume. So that would be how much? That would be, let's say, this is delta Q by delta T, right? And we are taking at 1 mole. So mu is 1, right? This mu is, so this is C, right, at a constant volume. So let us calculate this thing, right, in here. What would be this thing? So if we divide this by delta T, right, delta Q by delta T in equation first, let us take the change with respect to temperature at constant volume, right? So at constant volume, which term would be zero? What about this term? At constant volume, what would be this term? P is constant. Volume is constant. So if you take the change in V, this would be zero, right? Because volume
Yeah.
is constant. So if we take the change in volume, because volume is constant, so V minus V, V is constant, right? So this would be zero. So the second term is zero. So you will get delta Q by delta T, right?
Yes, sir.
And this is your delta U by delta T. And let's remove this subscript, right? So this delta Q by delta T is how much? That is CV. This is equal to delta U by delta T. Okay. Now let us talk about the change in right at constant pressure. So let us again using equation first at constant pressure. This would be how much? So this is delta Q by delta T, right? At constant pressure, and this is delta U by delta T at constant pressure, and this is P delta V by delta T, right? You are taking with respect to time, and this is at constant pressure. Because this pressure is constant, you can take it outside, right? This is the relation that you will get, and we can write the change in energy with respect to temperature at constant volume. This would be equal to change in energy, right, with respect to temperature at constant pressure. So these are equal, right? These are equal. So what is this thing? What is this thing? Delta Q by delta T. What is this? Delta Q by delta T. Yes, what is delta Q by delta T? What is the specific heat? Molar specific heat is 1 by mu delta Q by delta T. Right? If mu is 1, so C is delta Q by delta T. That is molar specific heat, right?
Yes.
So delta Q by delta T is molar heat capacity. And this is at constant pressure. And this is delta U by delta T at constant pressure. What about this thing? So now to solve this thing, let us use PV equals to mu RT, but mu is 1, so we can write RT. Now let us take change in what? Because pressure is constant, so this is P delta V, and this is R is constant, so this would be delta T. So if we calculate P delta V by delta T at constant pressure, right? This is simply R. Right? Pk we can take outside, so this is P delta V by delta T at constant pressure, that is equal to R. So this thing is how much? This thing is R. And we can remove this subscript, so this we have already seen, so that is C. So you will get Cp minus Cp equals to 1. So that is how it is it clear to you?
Yes, sir.
Yeah. Then please note it down, and then we'll talk about thermodynamic and if you have any confusion, please tell me, because these are very simple and these are, yeah, this can be confusing, but these are very simple. Right? So if we miss something, then it would be very confusing. But if you have doubt, please tell me. First thing that we have to understand that this C is molar specific heat capacity, right? So this is simply 1 by mu delta Q by delta T. But we are taking 1 mole in our example, so this is simply delta Q by delta T. And if we are talking about constant pressure, so we have to put the subscript P. If we have to talk about constant volume, so that we have to take the subscript V. So That is the only thing that we have. Okay, yeah, note it down and then we'll talk about thermodynamic processes. Which point
Done, sir.
then you have noted down all these parts.
No, sir.
Yeah.
Sir,
Yes,
why we took that P common?
P common. Oh, yeah, in here.
Yes, sir.
Because we know that this thing is constant pressure. So this is happening at constant pressure. So there is
Yes,
no
sir.
change in pressure. So we can take it outside of this box, right? Outside of this bracket. Let's take
Okay,
it here.
sir.
So let's say you are taking the differentiation in, let's say, some k and let's say y. This k is constant. So you can take it outside of the differentiation, right?
Yes, sir.
So that is what we are doing. We are taking the change. So we are taking the change in P del P and we are taking the change. We are taking change in both the sides, right? So we know that this P is constant, so it will come outside, and this R is constant, so this will come outside. So then you can write delta V by delta T, and that is R. That is what we have got. Clear?
Okay, sir. Yes, sir.
Noted.
Yes, sir. Done, sir.
Okay, so now let us talk about thermodynamic process. and then this chapter. We have to just remember all those important relations, Cv minus Cv equals to R, and first law of thermodynamics, law, and second law, and then we have so mainly we have four processes, and we have to just talk about them. And remember, the equations that we will use, so whatever we have done so far, right? All those equations we will use, but only some conditions we will apply, right? We will apply some conditions, and then we'll talk about the thermodynamic process. What are the processes? First one is the simplest one, isocycle. The second one is adiabatic. The third one is isobaric, isobaric, and then iso. Right. So just to remember, in this one, temperature will be constant. In this one, heat will be constant. In this one, what would be constant? Bar is right. So this is related to pressure. Pressure would be constant. 4, right? So this is volume would be constant. These are the four thermodynamic processes, right? And let us first talk about this isothermal, isothermal process. So in this process, temperature of the system remains constant. So then what would be the water, right? So let's say you have this system, right? These gases and you have this piston. And what you are doing is that you are pushing this piston downwards. So you are increasing the pressure of this gas. You are decreasing the volume, but you are doing this process in such a way that your temperature of this system is constant. So your pressure and volume, they are changing, right? Pressure and volume are changing, but the temperature is constant. So is it clear to you?
Yes, sir.
Yeah. Then what would be the ideal gas equations? What would be the equation of state? So from equation of state, right? What do we have? We have PV equals to mu or so if this T is constant, if T is constant, right? Then what happens? Mu is constant, R is constant, T is constant. Then your PV would be what? That would be constant. Here.
Yes, sir.
Okay, so your PV is constant. Let's say that this is correct. So PV is constant. Now, what would be the work done in isothermal process? Work done in isothermal process. Is, what we know that small work done. This is P, right? And we can write, right? So if we have want to calculate the work done, so this would be simply integration of from V1, right? Am I correct? Yes.
Yes, sir.
Now you see that from where I can get this value of pressure in terms of volume. So let us go back to this part, right? Let's say this is the first equation. So if we write, if we want to calculate pressure, so what would be pressure from this one? What would be pressure?
0.
From here, we want to calculate pressure. Why this would be zero? This is K by V, right? Here.
Yes, sir.
So this is K by V. Then we can put this value in here. So this is work done from V1 to V2, and this is K by V. So remember, K is constant, right? K is constant. We can take it outside. This is V1 by V2, and this is V. So what is the integration of 1 by, what would be the integration of 1 by V dV? This is exactly like 1 by X dx. What is this integration? Yes, what is this integration? Yeah, so yes, you got disconnected, right? Yeah, you got disconnected now. So what is the integration 1 by X? This is ln X, right?
Yes, sir.
Similarly, we can write this as what? This is K ln of V, and the limit is what? This is V2 and V. So if we write this thing, this would be ln of V2 minus ln of V1. And we know that we can write this negative as division. So this is K ln V2 by V1, right? So we know that what is this K? So this K was mu R T ln V2 minus V. So this is the work done in an isothermal process, right? So what do we know about isothermal process? That the temperature is constant, right? Temperature is constant, so your PV would be constant, and then work done in the isothermal process would be. These are the things we know about isothermal. So quickly note it down, and then we will talk about the other processes. Quickly, and if you have any doubt, please tell me. Yeah, whenever you want me to scroll down this.
Done, sir.
Then is that Yeah, noted.
Done, sir.
This was about the isothermal process. We'll talk about the other processes next class because that will not take that much of your time, right? In the next class, we'll talk about adiabatic process. But let us write the idea that what would be that adiabatic process. So in this one, heat will be zero, right? So change in heat that is zero, and then we have to also. So if this heat is zero, which means that delta Q equals to delta U plus delta V. So this is zero, which means that delta U is minus delta. This would be the adiabatic process, right? And yeah, we'll also talk about work done in the adiabatic process.